You see, this is not optimized. Yeah. This should say, it has to say. I only wanted to show you that you are possible with this program to construct a two windings reactor, because you have 8 different sizes. You can add this. This is a real construction. We can speak to her. I want, well, maybe have to look into the program. I want to speak to you in this afternoon about the triangulated system. This is very important because it is an easy way to point B. And tomorrow in the morning I want to discuss with you reactance design of existing furnace. I hope you have to show me something from your company. We can discuss, and I also have an example. This is PRF9, yeah, of an existing furnace, and I want to speak tomorrow in the afternoon about delta star connection. This is very important, and I also have a delta star connection which can damage the furnace transformer. This is very important that you should need that. And what you see here is PRF9, and point C is PRF7. What we have here, PRF, the bar example is PRF7. Okay. Yesterday I spoke in the evening to Professor Ahlers, and as he said to me, I never have done this before in my life, to speak so long and so clear and so intensive with people about construction of high current system. And he was very lucky about the discussion. Is that clear? Do you are too? You are happy about this long voyage to Germany? Can this help for you? Yeah. But I think it's good that there are two who can discuss. Yeah. One alone is not good, because if you are showing all what you have done, and nobody with your presentation, nobody is understanding what you are doing, it's very hard for you. Because you are responsible for all. And all you are sitting there and say, oh yes, do that, nobody is responsible.
That's right.
And therefore it's good that there are two. And you may show something, and he can also discuss with you.
Okay.
Yeah, this is very important. Okay. I now would like, time is going very, very fast. I would like to discuss with you about the triangulated system. Okay. The problem is 1, 2, 3. The reactance of the outside phase, x1, is x11 minus x12 plus x23 minus x31. For this, x3 is self-reactance minus 631 plus x12 minus x23. Okay, I make my doctor thesis with this in 1970. This is 43 years ago. And this year was born my second boy. And this is important. X2 is self-reactance minus x23 plus x31 minus x12. And you see, this is x12 and this is x23, and these both are high. You put from this self-reactance high values, and x31, this is this. x31, this x31 is low. And the idea for the triangulated system, we must move this, and this would not change, x31. But if we move this in this direction, then x3, 2, 3 and x1, 2 is getting lower. The coupling is getting lower. x1, 2 is lower, and also x2, 3 is getting lower, and x31 is constant. 1, 2, 3. We have moved this in this direction. Okay? And you see, if this is getting lower and this is getting lower, then x2 is getting higher. This is the idea. And if this is in the same edge of a triangle system, then x1, 2 is x2, 3 is x3, 1, and then x1 is x11 minus x12, and this is the same as this. We call this triangulation. This is triangulation. Okay? Every kind of a current system can be constructed as a triangulated system. Everything. I've seen examples, showed you some examples. The example should start It's a furnace transformer, triangulated, and should go over the total high current system, over flexible cables and over the high current system. I've shown you some. This is a triangulated system, and for this part, yeah, this is a half triangulated system, and yeah, you see other possibilities to try reactance symmetry. This idea is from this idea number 4. (1923). 90 years ago, they intended to increase the coupling between the outside phases by this magnetic system. Yeah, what they wanted to increase this higher, make this higher. Yeah, by this construction. This does not work. Yeah, this is a transformer. And they also used this system. This is a gap. This is an iron core. Yeah, and this is a high current bus. What happens if you have this? The gap is 2 centimeters. What happens if you make this a construction? There's a high magnetic field in the iron core because of the high permeability, and there are big forces in this gap, large forces, and I have collected these forces. They are in the middle 50 kilonewton. And you must put good material between non-magnetic material, because if you do not do that, the gap is zero, and the iron gets into saturation. This does not work, and this is much more expensive for getting higher reactance than a little loop. Nobody has had the idea with a current loop, and we made an invention, Alas, Tim and another, but this invention is over. It's now free. These are constructions with low impedance lines. These are low impedance lines. This may be knapsack area in the chemical industry. 3 transformers, and also they have 3 transformers around this furnace, very, very low reactances, and this is connected for steel. The point, these are 6 lines. You need 6 flexible cables, and you need 4 hydraulic systems, one for this, and 2 for the outside phase, or for the middle phase, and we call this knapsack connection for steel plants. And there were some of these constructions in Switzerland, especially. I calculated the high construction by hand, and it was 1.5 millions. And when they made a new construction, I said, do not make this. The reactance is too small, and the forces and the short circuit currents are too high. And if they switched the system on, it did not work, because they had so much forces that the electrode brake increased. Yes, I have. This is, you understand this. Yes, like this too. This is also possible. These are always. There are many applications also this. Phase 1, phase 3, phase 2. Yeah. And I've made a publication about this. This is a Fuchs system. You know this. And you see here, this is a Kappa-cooled system. Kappa-cooled system, which is not used today. Well, this is a typical reactor on the middle phase. This was the first design. This was not great enough, and they made a modification. And this is my first equation. Okay. Now these are some examples for receiving symmetrical current system. About this we want to speak tomorrow. Now we would like to speak about the triangulated system. We have an example in our computer. I think this is the number triangulated system 4. File number 4. We have a look on the controlling system here. You see, this is a triangulated system. This triangulated system is comparable to that picture of the instruction manual. We have seen that. You see that? On page 36. This was before there was the construction of electrode, copper-plated electrode arms. You see, we start here, but on the same position, but with this transformer, we can start here. Yeah, if you use the transformer, you remember the picture. You can start here. This is the typical transformer connection, the flexible cables. All are in a triangle. You see the middle phase, in each part there's a triangle. This is not here. And also here, this is a two tubes system with two cylindrical tubes. This is a little bit different from this. Yeah, it's the middle phase, the outside phase. What is the difference of this? The difference is, if you look into the picture, you can find that in the outside phases, the two tubes are vertical. The position of the two tubes is vertical. 6. 7. Yeah? You see, that the example on page 27 you have A, B, C. No. This is the example of the program, and the example here looks so. See that? They are vertically. You see that?
Yeah.
Ah. Okay. The picture on page 27. A, B, C. Yes. Now I have a question. What do you think? Are there different solutions by this or by this? The distance is the same. This distance and this distance. Well, we have calculated this. There is no big difference between this solution and this solution. Yeah. This is clear that in the middle phase you have the parallel and this is dependent from the situation. I think this is also clear. You see the transformer connection over there and the connection to the graphite electrode. This is, if you have this system,
I think this is good.
this is good.
Yeah.
But the calculation, if you calculate this by hand or this by hand, the solution is nearly the same. There's no difference. Yeah.
This time?
This is this. You see the vertical, this is better to fix it. This is the one leg, this is the other arm. Yeah? This is the arm, or the whole arm. But what I will discuss with you may happen that these tubes can make, there is a danger with mechanical oscillations. Like the system from the music. Yeah? All these parts have an own eigenfrequency. All have the eigenfrequency, and we have made some measurements in the Hamburg steel plants before. This was the code holder. And we found that these, here they are fixed, that these did not have a long lifetime. The oscillations made this defect. And we found that the eigenfrequency, mechanical eigenfrequencies, which have the same frequency than the forces of the electromagnetic current. Yeah, you have a big, if you have two wires, you can have electromagnetic forces which may have the same frequency than the mechanical eigenfrequency. And then it began to vibrate so that you can hear it in the steel plant. Yeah, and I will show you some frequency analysis of the harmonic current of a steel plant. The book. This is my book of personal publications for a long period of years. These are measured arc voltages and arc currents in a furnace. And you see there's an harmonic amplitude variation of the voltage between 400 volts and 0. 0 means the electrode hits the scrap. And this is a frequency of 5 cycles per second. And in the outside phase, there's a frequency half, 2.5 cycles per second. In the phase 1, there's no oscillation. And this is going to the current. The current has also an oscillation. And if you calculate the forces given by the current, you see also the oscillation in phase 1. Yeah, in phase 1 in two directions, and you see that the forces, electromagnetic forces, may have amplitudes up to 2000 Newton. And these forces are given by the current. This increasing current, the forces are increasing. The forces are proportional to the current and proportional to the external field, and then the things begin to move. There's another paper. We have measured the oscillations with these in the three directions with velocity, velocity measured this. This was water cooled, you see that, and these were the forces of a current with harmonic amplitude transmission, and this is the direction of the forces. These are the electrodes. The forces go outside to the wall of the furnace, and they try to move the electrodes outside. Also, there are forces on the arc. Therefore, the arc is burning into the direction of the wall. And therefore, you can calculate this, and then you can measure the frequency of the mechanical oscillation of the electrodes. And these are only electrodes. You also have electromechanical, these are low frequency, some cycles per second. You have high frequency electromagnetic forces, because I'm trying to find Yeah. Yeah, this is from the voltage you have 50 cycles per second, harmonics, third harmonics, fifth harmonics, and you have side amplitudes. This is the amplitude modulation of this, and these lower and higher frequencies are also in the current, and they are also in the forces who are going to these tubes. And there can be 100, 200 cycles per second higher frequency. They are identical with the forces of the acting current, electromagnetic forces, and they began to oscillate with their eigenfrequency, mechanical eigenfrequency. Therefore, this can destroy this. We do not have this in copper conducting electrode arms. We do not have this. This is one of the reasons, one of the advantages for copper conducting electrode arms. Okay? Yeah, this is what I want to say to you about here's another construction you can see. This is your reactor on the connection, transformer connection. Yeah, this is very high. You've seen that? We can speak about this construction tomorrow. This is the construction I will show and what the reason is. You can see also this here, this construction, and there is also, I think this is, if you have troubleshooting in this part, in this connection between the electrode arm and the graphite electrode. Yeah, this, you see, this is here free. Yeah, it's free. There's much trouble in older connections, and therefore they made the maintenance through this, also in this direction, through this here, and from here. This may be the reason for this appendix here. I do not know what can this have for a reason. You don't know more than I? No? Yeah? Okay. Okay. This has advantages and disadvantages. The disadvantages, this costs money. The advantage is all electrode can move in the same position.
Yeah.
Yeah, you do not need a longer hydraulic system, and you can have, you see that, yeah, parallel. This is a very good construction. You see also there's this here, and I think they make maintenance from this side if the connection is bad here. Yeah. Okay. Okay, this is what I want to say about, you see, the result of this system. The result is this system has symmetrical reactances, very, very good. The system, the graphite electrode also, and also on the electrode arm, the middle phase is a little bit higher. In the flexible cables, the middle phase has a lower reactance, and in the transformer connection, the first part is also higher in the middle phase, and this is, I think, it's a good construction, but it is needed. They do not use copper conducting electrode arms. Okay, you have questions to this. Please take questions. We have enough time, a lot of time. See the polling dimensions. Yeah. Okay. This is number 7. And we have the triangulated, the standard with electron arm reactor and the unsymmetric standard construction. Okay.
Reactance deviation from mean value.
Yeah.
That's
The mean value,
yeah.
mean value is this. Yeah. Some people also divide the maximum through the minimum,
Yeah.
but it's different from company to company. Here should stand the lowest value, therefore the lowest value is if you make the deviation from the mean value.
That is 0 is okay, good.
Yeah? It's dependent from what the customer wants. Yeah? I don't know, it's... what I want to discuss with you, do you know how you can measure a reactance?
Yes, I sent the mail.
Did
Total reactors in all.
Yeah?
Yeah.
But how can you measure this if you have an existing furnace?
Yes, this
Do you
is. I calculate the total reactors in all, but I don't know this is good or bad. Yeah.
No, my question is another question. Now we should have enough material for tomorrow. Tomorrow we should discuss about existing systems. I have one, and he has one, and we shall discuss about the delta connection. Yeah, this is very difficult. What we can make from MISTIC. I wanted to discuss with you the question, do you know how you have an existing furnace and you should try to make a measurement of the high current system with short circuit measurements. You did not make this. No, I will show you. I will discuss with you. This is new. Okay. I have made measurements to several furnaces, and I will discuss with you how to make a measurement You make measurements with short circuit attempts. You try to use a very low voltage and put the electrode into the molten bath. Yeah? And then you get only the loss resistance and the short circuit reactance. X1, X2, X3. Loss resistances are RV1. Ah ja, genau.
Okay.
Hallo. Hallo Leute. Ich sollte einmal vorbeikommen und Getränke abfragen.
Sind Sie der Herr Menz?
Ich bin der Herr Menz, genau.
Ja,
richtig.
gut, dass wir uns mal treffen.
Ja.
Ich habe das immer mit dem Herrn Schubert zu tun.
Genau,
Wir sind
richtig.
eigentlich sehr zufrieden mit
Ja.
dem Service hier. Wir gehen auch ganz unten immer Mittagessen.
Ja.
Das reicht völlig aus.
Ja.
Und es hat bisher wunderschön geklappt. Wir sind heute Montag, den 3. Tag.
Genau, richtig.
Wir hoffen, dass am Freitag, wenn die wieder wegfliegen, die beiden nachmittags,
Ja.
wir räumen hier Mittag 11 Uhr weg.
Ja.
Dass
Also,
der nicht gestreikt wird auf dem Flughafen.
Ja. Nee, also wir haben gerade Info bekommen, dass wohl jetzt der Rest der Woche nicht mehr gestreikt wird in Hamburg.
Aha, das wäre natürlich wunderschön. Sonst hätten die beiden eben im Zug nach Frankfurt fahren können, ja.
Ja.
Und aber sonst klappt das ganz gut. Wir haben auch einigermaßen erträgliches Wetter,
Richtig,
kein
genau.
Schneesturm
Ja.
und so weiter. Und zuerst hat uns ja der Herr Schubert betreut und dann war
genau.
hier eine Dame,
Ja.
immer sehr freundlich und
Ja.
regelmäßig. Das hat eigentlich recht gut geklappt. Auch so diese Möglichkeit hier, wie Sie
Ja.
sehen, nur mit dem Beamer. Und leider sollten ja 4 kommen.
Ja.
4 hätten wir wunderschön unterbringen
Ja.
können in diesen Räumlichkeiten. Und ich hätte gerne wieder, mein Kaffee ist kalt oder alles.
Ja. Nochmal eine normale Tasse Kaffee?
Kännchen-Kaffee.
Oder soll ich Ihnen so eine Kanne Kaffee hochbringen? Das kann ich auch machen. Oder hätten Sie gerne wieder so einen schönen aus dem Wiener Kaffee?
Ich weiß es nicht. Hier ist nichts mehr drin. You want also a cup of coffee?
No, that's okay.
No.
Kaffee? Ja?
Ja.
2000 Kaffee?
Ja, Tassen. Ja, das ist 2000 Kaffee.
Ja? Okay.
Das geht auf meine Rechnung.
Buche ich dann?
Bei mir mit drauf.
Ja, das kriegen wir hin. Das ist kein Problem. Irgendwie noch eine Flasche Wasser oder irgendwas dazu?
Nein, wir haben auch die da steht, noch gar nicht angebrochen.
Okay.
Ja, und nachher wollen wir ein bisschen durch die Stadt laufen.
Ja. Okay.
Okay?
Ja,
Und alles sonst in Ordnung? Noch Fragen von Ihnen?
alles wunderbar.
Ja, wir sind auch sehr zufrieden.
Ja,
Man kann ja hier mal rausgucken, wenn
Genau,
man
richtig.
Weile hat
ja.
und so weiter.
Genau, man kann ja auch rausgehen.
Die beiden haben vorgeschlagen, da in der Richtung, da in dieser Parallelstadt ist ein Italiener, wo man alles essen kann.
Ja, richtig. Casa della Roma.
Ah, haben Sie gesagt.
Ja.
Kann man da hingehen?
Also bis jetzt habe ich nur Positives von dem Laden gehört.
Die
Ich fand,
Casa
das ist-
della Roma.
Genau, richtig.
Ja.
Das ist, wenn man runtergeht und dann rechts.
Ja.
Genau, und dann
Also
also
er hat
rechts
den Vorschlag gemacht. Die
Genau,
wollen-
richtig. Rechts und dann kommt das dann ziemlich dann schnell auf der rechten Seite.
Ja, ja. Okay, da wollen wir mal hingehen.
Ja.
Man muss ja immer so ein bisschen sich bewegen.
Genau, das stimmt.
Okay?
Ja, wunderbar. Dann komme ich gleich wieder mit den 2000
Ja,
Kaffee.
okay, ist in
Ja?
Ordnung.
Sehr gerne. Bis gleich.
So, now we want to discuss how can get this. Short circuit, then this is a minimum. It should be equal to the calculation. These are the loss resistances. Yeah, this is also, these are about 0.3 to 0.35 milliohms with copper conducting electrodes, yeah, copper conducting arms. This is about 0.5 milliohms with tubes. on electrode holder. Now I will show how this works. If you want to measure this, 1, 2, 3, it would be the easiest way to make a measurement of current, of voltage and power.
Yeah.
And then if you measure the current, the power and the voltage we have for this electronic meters. Yeah? And you have here an X and a resistance, then the formulas are the impedance is voltage divided through the current is what's the square root from x squared plus r squared. Yeah. The resistance is the measured power divided through the square of the current. Then we have this, and then we have x given from this equation, Wurzel aus z Quadrat minus r Quadrat, Wurzel aus u durch I minus r Quadrat. There you get the loss resistance and the reactance. This is the idea. But it is not so easy. Where can we measure? On the primary side of the furnace transformer or on the high current side? To measure on the high current side is not easy because you cannot measure exactly the current. The most results are given on the primary side of the furnace transformer. Then you get the resistance of both. It's good if the connection is triangle, triangle, 0 or star, star, 0 or so. Then these currents are proportional to this current. And this current is proportional to this current. And you see there here 3 current measurements, 3 power measurements and 3 voltage measurements. And then you make, it is not possible to measure this point 0 because you say I measure this voltage because if you make Wir sind ja auch schon mal mit dem Stahlzentrum gewesen.
Okay.
Haben Sie das organisiert?
Mit dem Stahlzentrum?
Aus Düsseldorf.
Wann
Habe
war
ich schon mal ein Seminar, 5 Jahre oder so.
Nee, da war ich noch nicht hier.
Da waren Sie noch nicht
Ich
hier.
bin seit 2 Jahren.
Früher sind wir immer zu dem Hotel gegangen, das hier da in Moorfleet in der Nähe der Autobahn ist.
Okay.
Böttchershof.
Böttcherhof,
Ja,
ja.
ja, die haben auch. Und dann ist der entsprechende Leiter hier gegangen und sagt, das ist hier viel besser,
Okay.
weil sie zentraler liegen.
Ja.
Und er fand auch den Service recht gut, finde ich auch.
Okay.
Gut.
Ja, das freut uns doch zu hören.
Und insofern werden wir wohl immer wieder kommen.
Ja.
Ich habe also seit 1982,
Ja.
mit 30 Jahre lang, diese Seminare geleitet.
Okay.
In ganz Deutschland, auch im
Ja.
europäischen Ausland,
Mhm.
Schweiz und Luxemburg.
Okay.
Insofern weiß ich ein bisschen Bescheid, wie das so läuft.
Ja.
Und viele Hotels haben sich eben auf solche kleinen
Mhm.
Seminare eingerichtet.
Ja.
Sie ja auch.
Ja, wir hatten ja die 5 Suiten, auf jeder Etage eine.
Ja.
Und dann haben wir unten noch 6 Veranstaltungsräume,
Ja.
die wir ja auch variabel miteinander kombinieren können.
Ja, ja,
Machen.
sodass die Leute aus der ganzen Welt kommen. Hamburg
Ja.
ist ganz gut technisch erreichbar.
Ja, das stimmt.
Und insofern sind wir auch hierher gekommen.
Ja.
Das Einzige ist eben, dass die Umgebung hier nicht so...
Ja,
so
zwischen Hauptbahnhof und uns ist es halt noch ein bisschen
Ja,
multikulturell, sage ich mal.
und
Ne?
insofern muss man halt eben ein bisschen aufpassen hier.
Ja,
Und es scheint aber besser. Da drüben ist ja die Polizei, habe ich gesehen.
genau, richtig. Die laufen auf 4 Streife und gucken, dass das da nicht auch
Heute Mittag, heute Morgen, als ich kam, da standen da so lauter blonde Frauen vor ihrem Eingang
Ja.
und rauchten Zigaretten. Da habe ich dann gedacht, sind die von der horizontalen...
Ja, haben wir hier auch auf der Ecke und deswegen, also da wird jetzt auch momentan wieder stark gegen vorgegangen.
Habe ich denn ihr vorne am Empfang Bescheid gesagt? Haben sie gleich einen rausgeschickt.
Ja,
Und das darf natürlich nicht sein,
nee, das stimmt.
wenn die hier vor dem Eingang stehen.
Ja.
Bin mit der Taxe gekommen.
Ja,
Und insofern müssen sie da mitmachen beim Kampf. Und
ja, das machen wir
die
auf jeden
Polizei,
Fall.
die ist wohl auch zu Fuß sehr viel.
Ja, die machen es sind hier zu Fuß auf Streifen, auch also hier auf der Ecke, um da halt gegen vorzugehen. Ne?
Ja, das ist auch ganz richtig. Da leidet oder gewinnt auch ihr Hotel.
Ja, das stimmt.
Das müssen sie wirklich wissen.
Ja.
Und insofern, man ist ja hier sehr schnell in der Innenstadt.
Ja, das stimmt. Also
Und was mir eben gefällt, diese Möglichkeiten, dass man hier Meetings
Ja.
machen kann. Nicht? Wir sind hier die ganze Woche.
Ja.
Ja, und die sind extra gekommen aus Korea, damit wir ihnen ein bisschen was beibringen.
Ja.
Und deshalb auch die Wahl hier für dieses Hotel. Ja.
Ja. Nee,
Es tut
das
uns
stimmt.
leid, dass das immer so ein bisschen mit der Menge der rauf und runter gegangen
Ja.
ist, aber macht nichts.
Nö,
Kann ich
Da
nichts
sind
für.
wir flexibel.
Ja.
Was das
Okay, bedanke mich.
angeht. Bitteschön.
Ja. Sonst, wenn irgendwelche Fragen sind, ich weiß ja 2020 anrufen oder wie, ja?
Oder ne, einfach die 2000.
2000, das kann man nicht
Genau.
so merken.
Da kommt dann unter einer Rezeption dann raus, falls Sie noch mal was brauchen sollten.
Okay, ich bedanke mich.
Und sonst Kollege ist dann morgen früh wieder gegen 8:30 Uhr dann.
Der Kollege von Ihnen?
Ne, die Kollegin, die heute
Die
Morgen
Kollegin.
auch hier rum war.
Ah.
Die kommt dann morgen früh dann wieder vorbei
Ah.
und dann gegen 8:30 Uhr.
Ja. Haben Sie Ihre Seminarräume alle besetzt?
Wir sind voll ausgebucht die Woche.
Und gehen die Leute dann auch ins Hotel oder nutzen nur die
Nee,
Möglichkeit?
die schlafen. Also viele von den Herrschaften schlafen die Woche jetzt auch bei uns im
Da
Hause.
muss man sehr flexibel sein, denn einige kommen ja aus der Gegend hier,
Ja,
so wie ich.
ja,
Aber ich habe mich hier jetzt auch einquartiert,
Ja.
damit wir diese Position haben.
ja. Nee, selbstverständlich.
Ja, okay.
Ja.
Alles klar?
Ja, dann wünsche ich noch einen schönen Nachmittag.
Ja, danke schön. Herr
Und
Menz.
heute Abend guten Appetit dann beim Italiener.
Ja, wollen wir mal versuchen.
Ja, richtig. Und wir sehen uns dann spätestens morgen wieder.
Ja, ist in
Ja?
Ordnung.
Okay.
Ich bedanke mich.
Bitte gern. Tschüss.
Okay. If you make a measurement, yeah, from this against this, and you think this is the voltage 1, 0, you can make a mistake because you have big magnetic fields and you cannot get this start point by measurement. There make a mistake because there is an additional voltage which is given by the big area of this measurement line. When I was young, I made some ideas about this. Yes, this was the start point of the furnace, and this was the start point of measurement. And that was a mistake. A mistake can be very much. If you make a measurement against this point, you have very much, and if you change this line, you get with every new line a new measurement point. And then you can have wrong power distribution and wrong voltages, and therefore you must make two-phase short circuit. Yeah, also means you can get this paper here, and these are these measurements. First electrode is thrown electrode 2 and 3 are dipped. And then you get these currents. These currents must be equal. Yeah, if this is 0, these are the voltages, 3 voltages, and these are the powers, the active powers. And then they make another attempt. If you put 3 and 1 into this, and the third. And then you get an equation, 3 equations for the sum of 2 and 3. And the sum of 3 and 1, and the sum of 1 and 2. And therefore, you get, if you have a measurement in this loop, you have the sum of x is the sum of r. And then you can get, by this equation, the single phase values, resistance and reactance on the primary side of the system, which are much higher, and then you must divide these values onto the secondary side with the square of the transformer ratio. This is the transformer ratio, 30 kV to 550 volts. This was the voltage of the short circuit test. And then you get these results, and these are the results of the system, and then you must calculate from the transformer reactance and the loss resistance of the transformer, and then you have the reactances, the measured reactances of the high current system, 2.7 million, 2.65 million, 2.87 million, the good construction, 0.05, 0.26, 0.38 million for the loss resistance, and these are from the transformer. These are the results. We have played by this. These are the values of the primary. This is calculated onto the secondary with this transformer ratios, and yes, you see, this is the total reactance and resistance of the secondary, and then we must put away this from the transformer. This is a real transformer. This is a real, this is the ideal transformer, yeah. This is the real transformer, this here together. And this is the result. This is the mean value of this, and you see, this was measured after changing the electrode holders to copper conducting system. Yeah? I've made this more than 20 years ago. Okay, if you want to have this, make a copy of this. Not from the first. You start here. Yeah. From here you can start. Make a photo. Okay. Make a photo now. Yeah.
Sure.
You can start. Please make a photo from this.
Okay.
The other pages.
Okay.
And this way, if you have this way, you have the exact values of measured short circuit reactor. Then you can compare it with your construction by the computer. And then the difference between the measured and the calculated, this is the factor, 10%. You understand, yes? But we also have made in a tent. I must tell to you. We also have made a measurement in a ladle furnace of Denmark, and we made with copper short circuit of the electrode tips. Yeah, and look. Yeah, we tried to make a short circuit with copper. Yeah, I made a short circuit with copper, a cold short circuit. And we make copper and close it together. And then we made a short circuit measurement. Do not make this with a copper short circuit. Don't make this. What happened? When we switched on, make a measurement, everything was good. But when we switched off, there was a big magnetic energy, 1/2 L E quadrat, in three phases. Magnetic energy was tried to switch off, and it is not possible if a system has a current to shut down the energy, and the energy system said, no, we do not allow within the shutdown the current E from the T. We do not allow this because there was induced a voltage L dE dt. You see, dE dt is infinitive. And what happened? There was a big induced voltage by the control shutdown, and this big voltage destroyed our measurement system. Pang! Everything was going down to the scrap. Don't make a cold short circuit attempt. Make it if you take very slowly the electrode into the molten bath. Okay? Is that good? Up here. Now we shall continue our discussion and we make at 4 o'clock down. Yeah? But I will not start with the program for tomorrow.
Yeah.
Then we have nothing tomorrow. Also, Professor Ahlers told me that you were faster yesterday than in his plan. And we also are faster today in the plan. Can you show me? You have one construction for tomorrow to show and to discuss your construction.